So we shall continue our discussion on Fourier transform, and we have seen last day that we have just introduced Fourier transform by making omega continuous. In case of Fourier series, we have seen that omega uh, happens in a discrete manner at harmonic components of omega 0. Now, in case of Fourier transform, of course, omega becomes continuous. So therefore, it is quite natural that Fourier transform will encompass both Fourier series and other both periodic and aperiodic signals. So Fourier transform exists for both periodic and aperiodic signal. So therefore, it's a much more general representation than the Fourier series. However, interpretation and sometimes computation of frequency power at discrete components, irrespective of all other components, become simpler if we interpret in terms of Fourier series, where we the application may require just the power computation at one or two components. But if the components distribution is not known, that we do not know beforehand at what omega the components are. So in that case, it is better to initially compute the Fourier transform and find the dominant components. And then we can go to Fourier series or any other kind of representation. So, for example, so this is an example of an aperiodic signal. So X is a aperiodic signal. So therefore, X j omega would be equal to, because ut is there, so minus infinity to plus infinity will become 0 to infinity. So e to the power minus at and exponential of minus j omega t dt. So this is 0 to infinity exponential of minus a plus j omega t dt. Now this, if we can integrate, so it will give minus 1 by 1 plus j omega exponential of minus a plus j omega t. So we can evaluate it at 0 and infinity, and we will get 1 by a plus j omega. So this is of course for a greater than 0, because for a less than 0 this becomes a positive exponential and not square summable. So however, Fourier series does not exist for this signal, because this is not a periodic signal. Similar example of another signal for which Fourier series does not exist is the most popular function is xt equal to delta t, xt equal to ut. For all such functions, actually Fourier series does not exist. So for this case, of course, we can write directly x j omega is equal to minus infinity to plus infinity delta t exponential of minus j omega t dt. And because delta t equal to 1 for omega for t equal to 0, so therefore it will be 1. So therefore in the Fourier transform domain, the transform becomes a constant. Now for periodic signal, of course, this delta t can be shifted in delta can be placed at, in the frequency domain.
Sir,
Yes.
sir, I am not able to understand, sir, what is the difference between Fourier series and Fourier transform?
No, Fourier series is summation of exponential of j omega naught k j omega naught t. Okay. And we have Fourier, so that's why there is a finite omega naught. In case of Fourier transform, it is xt exponential of minus j omega naught t, j omega t, where omega is constant. And in Fourier series, omega is k into omega naught. So for Fourier series, omega equal to k into omega naught, where omega naught has a finite value.
Sir, for previous example, why doesn't
Yes.
Fourier series?
Yeah.
Why doesn't Fourier series for this example e to the power minus 8 ut?
K is an integer. So this is for Fourier series. Whereas for Fourier transform, omega is continuous. Okay. And for Fourier transform, omega is continuous. So therefore, this k into omega naught, because omega naught tends to 0, that is our basic point of derivation to make omega continuous. And because omega is continuous, so we can synthesize both aperiodic and periodic signals through Fourier transform. Whereas we can synthesize only periodic signals through Fourier series, because this omega is equal to k omega naught. K is an integer, omega naught is a finite value. So only at discrete points we take the sample of the x j omega. Okay, and then that if we sum it as the as for xt. Okay, so therefore that's why it becomes Fourier series becomes a period, xt becomes a periodic signal, because sum of periodic signal is a periodic signal. Whereas by making
Sir?
this omega, yes.
Sir, can we say that Fourier series is a special case of Fourier transform?
Yes, we can call it Fourier series is a special case of Fourier transform, and Fourier transform is a special case of Laplace transform. Okay, I think those who are, you have already done, from most probably some of you, Laplace transform. And after the Puja vacation process, Anand will discuss about Laplace transform. So
Sorry, here continuous omega means we can take any continuous value, like no discrete values.
yeah, so that's why this is a continuous integration. Omega is a continuous variable. So
So it
we
is
do.
continuous integration over time. T.
So in say the basic difference is that, so this is a forward transform, okay, or analysis. This is also known as the analysis, Fourier analysis function, and this is known as the Fourier synthesis function. Okay, this is also known as the inverse transform, because from the frequency domain we are going to the time domain. So that's why it is called inverse transform popularly. But this is also known as synthesis, because we can synthesize xt in terms of the basis function exponential of j omega t, which in case of Fourier transform, it becomes a continuous function. So that's why this is an integration. And if you see the Fourier series in case of Fourier series, that is a summation. Okay, so xt becomes a summation. Where is it? I think somewhere we have written. So this is the Fourier series expansion. All right. Xt comes as a summation, whereas because the x j omega comes as an integration.
Okay, sir.
Okay, so that's I think we have, this becomes an integration, the xj omega somewhere we have determined. The AKs are determined through integrations. So xt is a summation, but AK we determine through integration. But in case of Fourier transform, because both are a continuous domain, so therefore here what happens? Both are integration. Both are integration. Okay. So of course, if we make the discrete time case, that is discrete time Fourier transform, again it will become summation, that we shall discuss next. So what we were discussing for periodic signals, delta functions, delta omega minus omega 0, appears at discrete values of omega. That is in this case, that is at omega equal to omega naught or any other values. So for example, if we have xj omega is equal to twice pi delta omega minus omega naught, xt will be given by the inverse Fourier transform, 1 by twice pi minus infinity to plus infinity, twice pi delta omega minus omega naught, exponential of j omega t d omega. So this delta function will be non-zero only at omega equal to omega naught. So therefore, this is non-zero only at omega equal to omega naught. So therefore, this is simply becomes exponential of j omega naught t. So So that is nothing but a complex exponential or two sinusoids, cosine and sine sinusoidal function of omega naught t. So which is a periodic function. So in general, if we want to manipulate periodic signals, so instead of doing the forward integrations, often people model it by the delta function placed at appropriate places. Now here, if I place a delta function either in the one delta function in the positive half or in the negative half, the xt becomes a complex exponential signal. But if I place delta functions at the to omega naught and minus omega naught, so then that becomes a real functions of either cosine or sine, depending on whether we are placing a even delta, two delta functions are even function or odd function. If they are odd function, it will become a sine function. If they are even function, it becomes a cosine function. So we have seen that for xt equal to sine omega naught t, we have seen Fourier series coefficients exist because this is a periodic one, and we have a1 1 by 2j and a minus 1 equal to minus 1 by 2j. So they appear at the complementary part. On the other hand, because the pi factor is there, so Fourier transform coefficient appear at omega equal to plus minus omega naught, and their values are just like the Fourier series. We have at omega naught, there it was, because we are doing 1 by twice pi, so that's why that half is gone, so it becomes pi by j and minus omega naught minus pi by j. So like that, periodic signals can be done very easily. Now we will go to the properties. The properties are very similar.
Sir,
Yes.
so pi by j will be minus pi j, right? So should it point upwards or downwards?
No, this is minus pi by j, and this
Minus
is
pi
plus.
by j is plus pi j.
This is plus pi by j.
No, sir. I'm saying that minus pi by j, if we multiply and divide with j, we get plus pi j. So on organ plane, we get it positive and it point upwards, right?
No. Here we are. This is just the value. Okay. This is not a complex plane. These are the magnitudes of the Fourier coefficients. So these are complex magnitudes. unlike say these are, we are not dealing with RJ plane, no. So this is or not, this is x j omega. This is x j omega and this is omega. We are not dealing with complex plane. So it
Sir?
is, these are simple, like say Fourier series, if we plot, those are values are 1 by 2j. I mean, in terms of k, if we plot, we have here 1 by 2j and minus 1 by 2j. So this is the values of AK. Okay. So we are plotting just the values of AK. It is nothing to do with the complex plane where this x-axis is real and y-axis is imaginary axis. For such cases, those can be like that. So say for some other signal, before going to writing down the properties, okay, one more example probably. Xj omega is delta omega plus delta omega minus pi plus delta omega minus 5. And ht equal to ut minus 2. Okay, so one part we can do it, xt we can evaluate easily, but for find xt, find yt, xt convolute ht. So we can find xt of course easily because delta functions are there. So delta omega minus pi. So first one would be 1 by twice pi dc value. Second would be exponential of minus j pi t, 1 by twice pi exponential of j pi t, and third one would be 1 by twice pi exponential of j5t. So this will be xt. Directly you can write it because those are delta functions given, xj omega. Now xt convolute
Sir?
y. Yes.
Sir, the value of delta is either 0 or 1, right?
Yes, yes. So it is in the frequency domain. So delta omega will be 0 for all other places except at omega equal to 0. Okay. So it will be 1 at or this one at this one. Now in the inverse transform we have 1 by twice pi integration minus infinity to plus infinity exponential e to the power j omega t dt. So therefore delta omega into that will give you 1 by twice pi. Understood? So
Okay,
therefore
sir.
this is minus infinity to plus infinity delta omega exponential of j omega t d omega. So this is the first component. This is 1 by twice pi. So this is equal to 1 by twice pi. So now ht is given. So h j omega we can find out. Now Can you tell this is periodic or non-periodic, xt?
So non-periodic.
Yes, why?
So because one has period rational and another has irrational, so no LCM is there.
There is no common period exist, so therefore this is non-periodic. So we can find out ht equal to this and hj omega. Exponential of minus j omega two sine omega by omega. That is from the transform of ut, and minus j omega is coming because of that ut minus 2. So yj omega is equal to xj omega hj omega. So that is equal to, because xj omega is a delta function, so whatever be the hj omega will be picked at the delta function. So it will pick delta omega. It will also pick delta omega minus 5. But because this sign is 0 at omega equal to pi, at omega equal to pi, hj omega is equal to 0.
So at omega equal to 0 also it is equal to 0.
Yes, yes.
The first term also I think we should not be sure.
Yeah. So yj omega is therefore delta omega plus delta omega minus 5. So yt.
At omega equal to 0, isn't this 0? Like,
Huh?
no, at omega equal to, oh no, it's equal to 2.
No, omega equal to pi, this is 0, no, this is 0. Omega equal to omega minus 5, omega equal to 5, this is not 0.
And 0 it is equal to 2. I think.
And at delta omega, actually what will happen at delta omega, because both tends to 0, delta by very basic definition of this delta function is that omega tends to 0. So at omega tends to 0, sine omega by omega, okay, that is equal to 1, and omega equal to 0, this tends to 0, this tends to 1.
That will 2.
So that's why this is equal to 1.
So there's a 2 term also.
Two terms, both are tending to 1. Okay. So that's why it is picking delta omega.
So it won't be 0, right? So it will be 2.
No, no, it won't be 0. It won't be 0.
No,
Oh, sorry, hj omega. Oh. Hj omega tends to
2, right? So because like there is 2 sine omega by omega.
2. Okay. Delta omega. Yeah. Tends to 2. And so then what was our, this was delta omega. This becoming 2 delta omega. 2 sine omega by omega is correct. Ut minus 2. Yeah, just check it. Okay. So if it becomes 2, then this becomes 2 delta omega. So it becomes 1 by twice pi into 2 plus 1 by
Sir,
2
could
pi.
you explain how have you written h of j omega?
Yes.
How have you written h of j omega?
Which one?
H of j omega.
H of j omega. H of j omega, ht is given, and we have the ut. For ut, actually, the Fourier transform can be is 1 by j omega plus pi into delta omega. This is pi of delta omega. So from this,
5 also h of j omega will have different value.
yes.
At 5, omega is equal to 5.
Hmm.
It will be e to power minus 5j 2 sine 5 by 5.
This one,
Yes, sir.
Yes, sir.
2 sine pi by pi.
5, sir, at delta
5.
omega minus 5. The second term in yj omega.
Delta omega minus 5. Okay. Exponential of j5t. 1 by twice pi is there. So we have a delay 5. So for delta omega, it is 1 by twice pi. Okay. So delta omega minus 5, we have exponential of j5t into 1 by twice pi.
So
Okay.
we can multiply x of j omega with h of j omega because x is just impulse. We just put the input, right? So it becomes h of j5.
So it will be h of j5 into delta omega.
So you're like,
So here we have put delta omega minus 5. So there, this is basically xj omega into hj omega. Xj omega was delta omega minus 5 and hj omega at omega equal to pi.
So means that omega equal to 5, we will get h of j5. That's what
H
they are
of
saying.
j5.
Yes, sir.
H of j5 will come into h of j5. Yeah. H of j5 will come.
so from that, how are we getting yt?
So, but then h of j5 value, what would be the h of j5 value? So, into the value of basically h of j5, will be a fixed value. Okay. So this multiplied by h of j5. So h of j5 is not a function of omega. So this will not come, this will come as a scalar quantity multiplied by 1 by twice pi. So just like for the delta omega function also, whatever this 2 function is kind due to that. But I will check afterwards whether this is correct. But I think it is correct. H of j5 will be there, and this delta omega minus 5, 1 by twice pi exponential of j5 by t. So this is a scalar quantity or complex, just complex value. It's not a variable. So therefore, it will not come as a function of t. It will be hj5 by twice pi. Okay. It's a simple complex value, not a variable. So thereby we can do it like this. I think now we can write down the properties.
So this 1 by j omega plus pi del omega, we just found out u of j omega, right?
Yes, it is u of j omega. This is u of j omega. So that can be found out by summation rule of infinite summation 0 to infinity. So properties are similar, all properties are similar. Similar to Fourier series for periodic functions. Periodic and aperiodic functions. So therefore, there, namely, first will be linearity, then time shift, then conjugate symmetry. So for linearity, we have ax j omega plus by j omega time shift exponential minus j omega t0. So often this is called the linear phase term because the magnitude is basically 1 and the phase is linearly varying with the slope of t0. Conjugate symmetry.
So that will be minus j omega t naught, right? So e raised to the power.
Yes, exponential of minus j omega t naught. X conjugate t is, if we take ft, that becomes x conjugate of minus j omega. So like that, and there are many properties. Those can be written. And the listing is there in the book also. Just few of them we will write. The differentiation is also similar. If we take the Fourier transform, it will be j omega x j omega. So the differential operator is replaced by j omega. In the Laplace domain, it is s, x, s. And in the integration is just the opposite or complementary. It will be 1 by j omega x j omega, but because it is integration, so some initial value will come into picture. Pi x0 into delta omega. Time scaling is also similar. One by mod A. So basically, the scale, the dimension, the time, and the dimension of frequency when scaled, so the effect is complementary. So here suppose compression, so in the frequency domain that becomes expansion and the vice versa. In general, time and frequency in the ideal sense, because they are through an infinite integration operators, so they are of complementary in nature. So that means anything we observe in time, specifically at a particular, yeah, at a particular time which is defined by a delta function, that becomes infinitely extended in the frequency domain. Okay, so just like the periodic function also, it is delta function in the frequency domain and periodic infinite in the frequency domain. So similarly, we have convolution. We have yt xt convolute ht. If we take Fourier transform, then yj omega is simply becomes xj omega into hj omega. Or in the Laplace domain, it becomes ys equal to xs into hs. So that's why many a time for connecting circuits or any other system in series, we express them in terms of Laplace function and simply multiply all their frequency responses together to get the overall frequency response. So on the other hand, multiplication in the Fourier domain becomes convolution. So this is S j omega convolute P j omega. So multiplication, of course, if we want to implement differentiation in frequency, that can be easily implemented by multiplying t with xt. And if we take the Fourier transform, so that becomes xj omega. Similarly, after taking Fourier transform, if we multiply something and then take inverse Fourier transform, it becomes a differentiation in the xt. So for complex signal where these are not well, xt cannot be differentiated easily. So in that case, we can take the Fourier transform, and especially for finite data of large length, so we can do it where we don't know the form of xt or xn. So in such cases, differentiation or integration can be implemented through Fourier transform, either in the continuous domain or in the discrete domain. So of course, there are functions where Fourier transform exists and Fourier series does not exist. Such function is there, that is the delta function is there. Then unit step function, exponential functions. So for all such, Fourier transform exists, but the Fourier series does not exist. So for example, if we want that use some differentiation property, like we have a differential equation d2 dt2 yt plus 4 d dt yt plus 3 yt is equal to d dt of xt plus 2xt. Now if we take the Fourier transform, this will be yj omega into the first term would be j omega square, second would be 4j omega plus 3 equal to xj omega. This one would be j omega plus 2. So therefore 8j omega is equal to yj omega by xj omega equal to j omega plus 2 divided by j omega square plus 4j omega plus 3. So this, if we expand it through partial fraction, this will be half by 1 plus j omega plus half by j omega through plus 3. So now this is in the form of ut. Okay, so ht 1 by 1 plus j omega, so that is the form 1 by j omega is ut, but exponential of minus at ut is 1 by a plus j omega. So that of course, so this gives half of exponential of minus t ut plus half of exponential of minus 3t ut. So this is if we have xt exponential of minus at ut, if we take Fourier transform, this becomes 1 by a plus j omega. Again, this is from that infinite sum rule after expanding this ut by doing that integration. I mean, of course, this one can be done by simple integration, that because here we had, this is from coming that exponential of minus at, exponential of minus j omega ttt, and because ut is there, so this will be 0 to infinity. So from that we can do that.
So here we are synthesizing ht from hj omega, right?
Okay, which one?
So ht here we synthesized from hj omega.
No, ht is synthesized from this differential equation. So this is the given a differential equation of a system, can be a circuit, can be anything, any mechanical system as well. So we have a differential equation, from that we are finding out impulse response. Okay, so given a circuit, we want to find impulse response. So this is the easy way to find the impulse response. We can do it either by through Laplace, that is hs equal to ys by xs, and then this will be s plus 2 by s square plus 4s plus 3, and partial fraction we can do half by 1 plus s, half by 3 plus s, and do the inverse Laplace transform. Or we can do the Fourier transform as well. So instead of s, we are writing here j omega. But in general, of course, Laplace transform is the more general case. Because that S represent, we have a both real part and complex part. And so in case of Fourier, we are having only the complex part. And if we compare both the representations, Laplace, this complex representation of Fourier transform is on a line, that is j omega axis if we take a complex plane, whereas the S plane is a both the real and imaginary both are involved.
So what I'm asking is ht is 1 by 2 pi that integral minus infinity to infinity. Did we do that here?
Yes.
Okay.
Okay. We are doing that, but here we have not, we have this expression exponential of minus at ut Fourier transform. Like for delta function, we have that delta t equal to 1, ut is 1 by j omega plus pi into delta omega. And if we put t, if we multiply it by t, so like say if we have t exponential of minus at ut, so because we have multiplied t, so what will happen? So this will be one by j omega square. So these are the some standard relations are there. Often we use it. Okay, for ut exponential of minus at, it is It can be evaluated by doing that integration.
Okay, sir. Means, sir, we knew some results, so we use them directly.
Yeah, you can use it.
T minus AT OT sir will be taking differentiation of 1 by 1 plus 1 by A plus j omega, right?
Yes.
There will be a j or minus j also, right? At the
No.
change the numerator.
Differentiation in frequency, that is txt. If we take Fourier transform, that is j dd omega of x j omega.
Yes, so differentiation with respect to omega of 1 by A plus j omega. So it becomes minus j by A plus j omega whole square.
Okay. I need to check it. Okay. So TAT, this we can do this thing, T exponential of minus AT. So you can evaluate it also through the integration. Of course, here we should put some condition that if A is a real part of A, greater than 0. For this also there is a condition, real part of A greater than 0. So this should be written explicitly. Okay, so I think you can solve few of the examples. Also, I have provided some some written notes in the some written notes also I have uploaded. So there are also some examples of the books that I have given, which are important. Mainly, I have kept taken those examples and given it there. Next, we shall discuss the discrete time Fourier transform.
Will the Fourier transform will also be there in the test?
Yes, that's why I have uploaded the note. No,
Sir,
maybe tomorrow we shall. I have uploaded the note beforehand. That's why.
Sir, the discrete time also.